Chapter 5, Probability Distributions. Here comes another hard one, so brace for impact. At first glance, this chapter looks pretty benign with only 3 sections. After all, it's short. But unless I'm pleasantly mistaken, a lot of students will struggle in 5.2, Probability Distributions. Once you get to 5.3, Binomial Distribution, you can breathe easier. As before, let me use my Mathematica notebook as a shortcut, and this time let's begin with a review. Let's begin with a non-empty set S, which we call a sample space. And any subset of that S is called an event. And a set function P defined with these following properties is going to be called a probability function. What is the first property? Any probabilities between 0 and 1 for any event. If you prefer percentages, then 0% and 100% respectively. Next, the probability of the empty set, in other words, the probability of an impossible event, is 0. The probability of the whole set, in other words, the probability of anything that goes, is the entire probability 1. Those were easy. The third one is the most fundamental and difficult to understand. The probability of a sequence of infinitely many mutually exclusive events, A1, A2, A3, and so on and so forth, is equal to the infinite sum of their probabilities. It's hard because we are dealing with infinite sums. If you have only finite sums, then, well, after A1 through AN, the rest will be all empty, so this infinite sum notation is more exclusive. And that is going to be really necessary when the sample space becomes infinite. Yes, we are going to deal with those kind of situations a lot from chapter 6 and on. Now let's move on to probability and logic. The easiest of the bunch is the complement, not A. You can easily see from this Venn diagram the probability and the probability of its complement add up to the full probability 1. So subtracting 1 or subtracting probability of A from 1, you get this formula. Probability of the complement event is 1 minus the probability of the original. Easy. Next one, a little bit harder but not too difficult. Probability of A or B corresponds to the probability of the union. So we have this kind of Venn diagram. Consequently, we can decompose this union like this and then simply add up the probabilities because they are all mutually exclusive. Or you can blindly add up 2 probabilities and then subtract away the part that are doubly counted. In particular, if the doubly counted part or the intersection is empty, in other words, there's nothing in this purple region right here, then you can simply add up the probability because they are disjoint or mutually exclusive. Now, hardest of the bunch is the intersection because we have 2 different aspects. Number 1, logical aspect. A and B correspond to the intersection. Okay, but is that it? Actually, no, there's more to it. A lot more. We have, in general, a multiplicative property like this. Probability of A and B is equal to probability of A times the probability of B given A. The second probability is a conditional probability. If you have independent events, then this conditional probability B given A is the same as the original probability of B because A and B are completely unrelated. So we have a little bit easier product. Examples, well, here we go. We can consider some earn models as before, and if we have selection without replacement, then the second selection, third selection, and so on, they are all conditional probabilities because they're affected by the previous draw. And we have some tree diagram like this, and whenever we have tree diagram, we use multiplication principle. as we follow the path from here to there, and then here and there, kind of like that, we just multiply the conditional probabilities. And this one goes on for many more steps actually. It's just that the tree diagram will just become more complicated, but the multiplication principle will remain the same. In particular, if we have independent events, well, we have actually the same tree diagram because we are following the same paths, but the probabilities are a little bit simpler. We don't have to consider conditional probabilities, just original, because conditional and original probabilities are the same. Well, I hope that was a good review for chapter 4, and let's move into now 5.1, random variable. What is a random variable? A random variable is a scheme that assigns a numerical value to each outcome of a sample space. So each element of the sample space has a unique numerical value. An example, well, let's go to an example 2.2. Let's consider an urn with 5 red balls and 3 green balls and 2 blue balls. Okay, we could consider different numbers, but well, here we go. We have a sample space RGB, and please note none of these is a number. They're just characters or they're just colors. However, it is possible that we assign certain number, kind of like payoff model or gambling model. For instance, if you draw a red ball, you earn nothing. A green ball, then you earn $2. If you are lucky enough to draw a blue ball, then you will earn $3. Another example, okay. If red ball comes out, then you have to pay $1.50. And green ball, then you earn 50 cents. A blue ball, then you earn $1. How about something like this? A red ball or green ball, in both cases, you have to pay $1.25. And if blue ball comes out, then you earn $4.75. Of course, you can consider different numbers, but in any case, you can assign numbers to each outcome. Consequently, you can express probabilities using algebraic expression, kind of like this. The probability that random variable x takes a value less than or equal to 2. X is less than or equal to 2. Well, here comes x. And for which colors we have less than or equal to 2? Well, these two, 0 or 2. So you just add up these two probabilities and you have this kind of computation. In other words, the random variable changed these probabilities associated to colors into probabilities associated to an algebraic expression. Let's do this one more time so that you can have a little bit better understanding. How about the next probability? The probability that the random variable y takes a value strictly greater than 0 but less than or equal to 1. How about these? Greater than 0, okay, 0.5 is greater than 0, and less than or equal to 1, so 1 is included. So what we get, you have to add up these two probabilities. Green and blue, they add up to 0.5. How about the next problem here? The probability that the random variable z takes a value negative 1.25. We are talking about these two cases, red or green. Add up, you get 0.8. Please compare that with problem A. You have the same probabilities because they're both red or green. Even though the algebraic expressions are different, of course, that's because we are dealing with different random variable, but they're all related to each other because we are dealing with the same sample space. Okay, the next topic we have to talk about is discrete random variable. A random variable x is called a discrete random variable if it takes only discrete set of values, such as integer values, but it's okay to have some non-integer values as long as they are discrete. Well, first example, roll a die and excuse me. Oh yes, 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 it is. It is a die casting model. Roll a die and count the number of dots. We have 1, 2, 3, 4, 5, or 6. We have a discrete random variable. Not only that, this is finite random variable. How about the next one? Toss a fair coin and assign pi for head and e for tail. Well, they look like very, very complicated real number with never ending and no apparent patterns. Another one like that, never ending decimal with no apparent pattern. But don't be fooled by those. We just have two numbers. They are discrete. How about C? All the random variables discussed in the previous example, this one, this one, this one, they're all discrete random variables. Duh. This one and that one have only 3 values. This one has only 2 values. They're all discrete. Next example, this one is a little bit more interesting because we can consider infinitely many different values. We can take any non-integer, excuse me, what am I talking about? We can take any non-negative integer value. Sorry, did I say non-integer value? Sorry about that. Non-negative integer values. 0, 1, 2, 3, 4, 5, and so on and so forth. However, they're all discrete. This kind of thing is an example of a discrete random variable too, even though there are infinitely many outcomes. By the way, this very random variable is called Poisson random variable, and I don't know whether we'll have time to discuss this example in this class or not. In some years, I ended up talking about Poisson random variable as an approximation of binomial distribution, which we're going to cover at the end of this chapter. In some semesters, due to time constraint, I had to skip. I don't know whether I will do that or not, but in any case, here it is. This thing is called Poisson random variable. By the way, for an advanced student, here is a precise mathematical description of a random variable. It is actually a real valued function defined on the sample space. In other words, each element of a sample space has a real value. So much for random variables 5.1. In the next video, we're going to start discussing probability distribution.